An inductor, also called a coil or reactor, is a passive two-terminal electrical component which resists changes in electric current passing through it. It consists of a conductor such as a wire, usually wound into a coil. Energy is stored in a magnetic field in the coil as long as current flows. When the current flowing through an inductor changes, the time-varying magnetic field induces a voltage in the conductor. According to Faraday's law of electromagnetic induction, according to Lenz's law, the direction of induced EMF is always such that it opposes the change in current that created it. As a result, inductors always oppose a change in current, in the same way that a flywheel opposes a change in rotational velocity. Care should be taken not to confuse this with the resistance provided by a resistor. An inductor is characterized by its inductance, the ratio of the voltage to the rate of change of current, which has units of henries. Inductors have values that typically range from 1 microhenry to 1 H. Many inductors have a magnetic core made of iron or ferrite inside the coil, which serves to increase the magnetic field and thus the inductance. Along with capacitors and resistors, inductors are one of the three passive linear circuit elements that make up electric circuits. Inductors are widely used in alternating current electronic equipment, particularly in radio equipment. They are used to block AC while allowing DC to pass. Inductors designed for this purpose are called chokes. They are also used in electronic filters to separate signals of different frequencies, and in combination with capacitors to make tuned circuits, used to tune radio and TV receivers. Overview. Inductance results from the magnetic field around a current-carrying conductor. The electric current through the conductor creates a magnetic flux. Mathematically speaking, inductance is determined by how much magnetic flux phi through the circuit is created by a given current. High inductors that have ferromagnetic cores are nonlinear. The inductance changes with the current. In this more general case, inductance is defined as any wire or other conductor will generate a magnetic field when current flows through it. So every conductor has some inductance. The inductance of a circuit depends on the geometry of the current path as well as the magnetic permeability of nearby materials. An inductor is a component consisting of a wire or other conductor shaped to increase the magnetic flux through the circuit, usually in the shape of a coil or helix. Winding the wire into a coil increases the number of times the magnetic flux lines link the circuit, increasing the field and thus the inductance. The more turns, the higher the inductance. The inductance also depends on the shape of the coil, separation of the turns, and many other factors. By adding a magnetic core, made of a ferromagnetic material like iron inside the coil, the magnetizing field from the coil will induce magnetization in the material, increasing the magnetic flux. Constitutive equation. Any change in the current through an inductor creates a changing flux, inducing a voltage across the inductor. By Faraday's law of induction, the voltage induced by any change in magnetic flux through the circuit is from above, so inductance is also a measure of the amount of electromotive force generated for a given rate of change of current. For example, an inductor with an inductance of 1 Henry produces an EMF of 1 volt when the current through the inductor changes at the rate of 1 ampere per second. This is usually taken to be the constitutive relation of the inductor. The dual of the inductor is the capacitor, which stores energy in an electric field rather than a magnetic field. Its current-voltage relation is obtained by exchanging current and voltage in the inductor equations and replacing L with the capacitance C. Lenz's law. The polarity of the induced voltage is given by Lenz's law, which states that it will be such as to oppose the change in current. For example, if the current through an inductor is increasing, the induced voltage will be positive at the terminal through which the current enters and negative at the terminal through which it leaves, tending to oppose the additional current. The energy from the external circuit necessary to overcome this potential hill is being stored in the magnetic field of the inductor. The inductor is said to be charging or energizing. If the current is decreasing, the induced voltage will be negative at the terminal through which the current enters and positive at the terminal through which it leaves, tending to maintain the current. Energy from the magnetic field is being returned to the circuit. The inductor is said to be discharging. Ideal and real inductors. In circuit theory, inductors are idealized as obeying the mathematical relation above precisely. An ideal inductor has inductance, but no resistance or capacitance, and does not dissipate or radiate energy. However, real inductors have side effects which cause their behavior to depart from this simple model. They have resistance and parasitic capacitance. At high frequencies, the capacitance begins to affect the inductor's behavior. At some frequency, real inductors behave as resonant circuits, becoming self-resonant. Above the resonant frequency, the capacitive reactance becomes the dominant part of the impedance. At higher frequencies, resistive losses in the windings increase due to skin effect and proximity effect. Inductors with ferromagnetic cores have additional energy losses due to hysteresis and eddy currents in the core, which increase with frequency. At high currents, iron core inductors also show gradual departure from ideal behavior due to nonlinearity caused by magnetic saturation of the core. An inductor may radiate electromagnetic energy into surrounding space and circuits, and may absorb electromagnetic emissions from other circuits, causing electromagnetic interference. Real-world inductor applications may consider these parasitic parameters as important as the inductance. Applications. Inductors are used extensively in analog circuits and signal processing. Applications range from the use of large inductors in power supplies, which in conjunction with filter capacitors remove residual hums known as the mains hum or other fluctuations from the direct current output, to the small inductance of the ferrite bead or torus installed around a cable to prevent radio frequency interference from being transmitted down the wire. Inductors are used as the energy storage device in many switched-mode power supplies to produce DC current. The inductor supplies energy to the circuit to keep current flowing during the off switching periods. An inductor connected to a capacitor forms a tuned circuit, which acts as a resonator for oscillating current. Tuned circuits are widely used in radio frequency equipment such as radio transmitters and receivers, as narrowband pass filters to select a single frequency from a composite signal, and in electronic oscillators to generate sinusoidal signals. Two inductors in proximity that have coupled magnetic flux form a transformer, which is a fundamental component of every electric utility power grid. The efficiency of a transformer may decrease as the frequency increases due to eddy currents in the core material and skin effect on the windings. The size of the core can be decreased at higher frequencies. For this reason, aircraft use 400 Hz alternating current rather than the usual 50 or 60 Hz, allowing a great saving in weight from the use of smaller transformers. Inductors are also employed in electrical transmission systems, where they are used to limit switching currents and fault currents. In this field, they are more commonly referred to as reactors, because inductors have complicated side effects which cause them to depart from ideal behavior, because they can radiate electromagnetic interference, and most of all because of their bulk which prevents them from being integrated on semiconductor chips. The use of inductors is declining in modern electronic devices, particularly compact portable devices. Real inductors are increasingly being replaced by active circuits such as the gyrator, which can synthesize inductance using capacitors. Inductor construction. An inductor usually consists of a coil of conducting material, typically insulated copper wire, wrapped around a core either of plastic or of a ferromagnetic material. The latter is called an iron core inductor. The high permeability of the ferromagnetic core increases the magnetic field and confines it closely to the inductor, thereby increasing the inductance. Low-frequency inductors are constructed like transformers, with cores of electrical steel laminated to prevent eddy currents. Soft ferrites are widely used for cores above audio frequencies, since they do not cause the large energy losses at high frequencies that ordinary iron alloys do. Inductors come in many shapes. Most are constructed as enamel-coated wire wrapped around a ferrite bobbin with wire exposed on the outside, while some enclose the wire completely in ferrite and are referred to as shielded. Some inductors have an adjustable core, which enables changing of the inductance. Inductors used to block very high frequencies are sometimes made by stringing a ferrite bead on a wire. Small inductors can be etched directly onto a printed circuit board by laying out the trace in a spiral pattern. Some such planar inductors use a planar core. Small-value inductors can also be built on integrated circuits using the same processes that are used to make transistors. Aluminium interconnect is typically used, laid out in a spiral coil pattern. However, the small dimensions limit the inductance, and it is far more common to use a circuit called a gyrator, that uses a capacitor and active components to behave similarly to an inductor.